Einstein field equations. In the general theory of relativity, the Einstein field equations, EFE, also known as Einstein's equations, relate the geometry of space-time to the distribution of matter within it. The equations were published by Albert Einstein in 1915 in the form of a tensor equation which related the local space-time curvature expressed by the Einstein tensor with the local energy, momentum, and stress within that space-time, expressed by the stress-energy tensor, analogously to the way that electromagnetic fields are related to the distribution of charges and currents via Maxwell's equations. The EFE relate the space-time geometry to the distribution of mass energy, momentum, and stress, that is, they determine the metric tensor of space-time for a given arrangement of stress, energy, momentum in the space-time. The relationship between the metric tensor and the Einstein tensor allows the EFA to be written as a set of nonlinear partial differential equations. When used in this way, the solutions of the EFE are the components of the metric tensor. The inertial trajectories of particles and radiation, geodesics, in the resulting geometry are then calculated using the geodesic equation, as well as implying local energy momentum conservation. The EFE reduced to Newton's law of gravitation in the limit of a weak gravitational field and velocities that are much less than the speed of light. Exact solutions for the EFE can only be found under simplifying assumptions such as symmetry. Special classes of exact solutions are most often studied since they model many gravitational phenomena, such as rotating black holes and the expanding universe. Further simplification is achieved in approximating the spacetime as having only small deviations from flat spacetime, leading to the linearized EFE. These equations are used to study phenomena such as gravitational waves. The expression on the left represents the curvature of spacetime as determined by the metric. The expression on the right represents the stress, energy, momentum content of spacetime. The EFE can then be interpreted as a set of equations dictating how stress, energy, momentum determines the curvature of spacetime. These equations form the core of the mathematical formulation of general relativity. They readily imply the geodesic equation, which dictates how freely falling test objects move through spacetime. The EFE is a tensor equation relating a set of symmetric 4 times 4 tensors. Each tensor has 10 independent components. The 4 Bianchi identities reduce the number of independent equations from 10 to 6, leaving the metric with 4 gauge fixing degrees of freedom, which correspond to the freedom to choose a coordinate system.